Okay, hi, Assalamualaikum and selamat tengah hari. So, these are my recording for the class that we have cancelled last week. Alright, so okay, so I share my screen. Okay, so I would like to continue this topic of the spherical triangle application. Okay, so okay. Alright, so this is the last part. Okay, I believe we can continue. Alright. Okay, so this is about the previous is about the rotation process for the moon's orbital, and we continue for a proper motion. Okay, so if you see for the proper motion is actually when we have many stars that show continuous changes in the position due to their angular velocity that relative to the other star, or this condition we call as the proper motion. Okay, so the proper motion of stars may be as large as several up seconds per year. Okay, and as you can see, this is the direction of where we have the perpendicular to line of sight and the parallel to our line of sight. So this refers to different velocity. Okay, and the point on the sky towards which the sun and the entire solar system move in our galaxy is called as the solar apex, while the direct opposite is called as solar antipodes. Okay, so stellar motion, okay, or the star itself seem to be directed away from this apex, but towards the antipodes, means towards the direct opposite. Okay, so the apparent motion of the sun towards the solar apex is actually we can say in that perspective effect, okay, that's similar to show how the meteor appear to radiate from a single point in the sky. Okay, so this this is because we are observing the motion from a moving reference Earth, and also the relative motion of the sun and the other stars that created the direction of movement. So the proper motion should be largest for stars that relatively close to us and should be essentially unmeasurable for very distant galaxy. So this is the example of on how to apply the proper motion correction to the precise coordinates. Okay, so this is the information given, okay, to estimate. Okay, so this is the total proper motion, which is simple by mu. So it's related to these two components, alpha and the sigma, where the phi, we call this symbol as phi. So phi is the position angle that can be calculated with this formula. Okay, now we come into the radial radial velocity. Okay, so the radial velocity is the component of stars motion that is along our line of sight, either towards or away from us. And this radial velocity can be measured by Doppler effect upon the light wave that have left the star that was predicted by Christian Doppler in 1842, but was unable uh, to measure it at that time. Okay, because maybe there are several information that they can have during that time, so they can't manage to do to apply that formula to get the radial velocity. And after that, suggested by this French physicist, that the wavelength of absorption lines in the stellar spectrum should be longer if the star is receding and shorter if the star is approaching. So William first observed the Doppler effect in a star in 1868 by measuring the redshift of the hydrogen F line with this wavelength in the spectrum of Sirius. And this measurement was made possible through the ability to make the photographic record of spectra, okay, in the late 18th. So the stellar radial velocity is one of the most precisely measurable astronomical quantities, being measured for bright star or at any distance and used to discover the exoplanet. And this is the formula of radial velocity, V over C, okay, and equals to the average of the Doppler shift lambda over the wavelength. And this formula assumes V is more or less than C. Okay, so V refer to line of sight of the velocity of the source relative to the observer. So now is the space velocity. So with the knowledge of proper motion and radial motion, okay, of star, so we still need to understand how to calculate the true motion, okay, through the space velocity. So the distance to the nearest star are the best determined using the trigonometric parallax. So we could use this as a baseline to see how the observed position of nearby star shift relative to the more distant background star. So we have these important distance units in astronomy. First is a kilometer, and then AU astronomical unit, and is defined as the distance between Earth and the Sun. And also light year, okay, LY, the distance light takes to travel in 365.25 days. Okay, and we should know about this parallax angle with theta p. It's measure the apparent shift in position of a relative nearby star against a more distant when viewed from a different angle. So you have 1 per second. It means this parallax of 1 arc second. Okay, the distance at which 1 AU that subtend an angle of 1 double prime. So the parallax angle is a crucial, I can say, crucial measurement, okay, in astronomy. It allows us to determine the distance to nearby stars by observing a star from different point, okay, in its orbit. So basically, astronomers can measure its apparent shift against the background of more distant stars. So this shift is known as the parallax. Okay, so this given the d distance, proper motion, the tangential velocity vt of a star, and it can be computed as that vt equals to mu d. So given the radial velocity VR, then the total space velocity is v. Okay, So this is the information lah for that space velocity formula. Okay, so now we reach the last part of this chapter is the refraction, aberration, and parallax. So what is the refraction? Okay, I believe you have heard about the refraction before. Okay, so it's the bending of a starlight as it passes through our atmosphere. And the further of star is from the zenith, means the higher the refraction. Means if you have a star posited at, you can observe it's posited at how you can say a different angle, not in zenith. Zenith means in 90 degree, but for the other angle means some kind of 50, 60 degree, okay, above the earth. So you got a smaller, is it the smaller refraction or the higher refraction? So it is related to the atmosphere where your line of sight of the source or the observer with the source lah. Source tu means your star lah yang you nak looking for. Okay, so a further a star from zenith means in the ufuk. Maksudnya dia bukan di 90 degree. So ideally di 50, 60, 30, 20, okay, away from zenith means it has a higher refraction lah. So dia nak go through the atmosphere tu area dia lebih banyak. And refraction dia pun akan lebih besar lah compared to star yang berada dekat atas tegak lah. Maksudnya yang betul-betul di 90 degree. So aberration of starlight is the deviation of star from its true position due to Earth's orbital motion. So in other words, the observed position of star is defined by the vector sum of the star's velocity and the apparent velocity which the outside world is moving away from us. Okay, so this aberration of starlight discovered by James Bradley, okay, in 1729, and the greatest amount of aberration occurs 90 degrees away from the direction of Earth's moving. And this is the formula for theta max, maximum aberration, okay, where we have tangent of theta max equal to V Earths over C. Okay, and now is parallax. What is parallax? Is the tiny movement in the apparent position of star due to Earth's changing position. So the parallactic displacement of star is inversely proportional to the distance from Earth to star, where we have pi equals to 1 over d. And the nearest star beyond our solar system is Proxima Centauri and has this parallactic shift. Okay, ini yang paling the nearest star lah beyond our solar system. So this is the Proxima Centauri. So the first stellar parallax were measured in 1838. Okay, so that's all about the application of the spherical triangle, and also additional with these three terms called refraction, aberration, and parallax. So I think I will stop here for first recording, and I will record for the other class. For the class we cancel on Friday. Okay, so I will upload the another one recording for the new chapter lah. Okay, thank you.